So this is a quick talk through of the Session4 MATLAB for OS105. If we have a look at the instructions, the aim of this session is to collate the vertical C2D profiles that we collected from the boat through the section that we were doing our spatial survey within, and then combine them together into a vertical section. So it's essentially looking side on at the water. So on the x-axis we've got the station number going from 1 to 5. On the y-axis we've got depth. And then what we're displaying here is the vertical structure through the water column, in this case of temperature. This is using what's called a p-color method for doing this display, and on the right hand side is using a filled contour method. So we'll look at how we can combine the data, load the data in, combine the data, and then produce this kind of plot that can help you interpret. As you can see here, we've got a fresh, very thin surface layer of, in this case, warmer water overlying the colder water underneath. You could then relate these with the spatial maps that you're compiling. So if you follow the steps to complete, I'm going to presume that you can download the zip archive of the profile data, which is available on the DLE, and I'm going to be working with a folder on my desktop. In MATLAB, we change the current directory to the new folder where we save the data, and within that there are data files containing profiles collected at 5 stations by each of the group throughout the field work. Positions of the stations are given in a text file that's also in that folder. And if you choose one section data, and we're going to work through to write a script to load, compile, and plot the data as shown below. There are a couple of hints. The data is in a text file which we can read with DLM read. We used that for loading in CCD data before in session 1, so that should all be familiar. So I'll go through that quite quickly. The header in each file specifies the exact time when the profiles were collected, so you'll know which section was collected when. And we need to collate the data from all the profiles that make up a section into a single matrix to then run either p-color or contour on the data. And to do that, we're going to create a function that takes averages. So the issue with an individual profile is that it collects a continuous stream of data as the instrument is being lowered to different depths. When we're creating either a p-color or a contour plot, MATLAB requires gridded data. So that means that we need to do some depth averaging of the data so that at regular intervals down through the water column, we're going to average the data into what are called depth bins. So we'll create depth bins between 0.5 meters and 1 meter, and then 1 meter and 1.5 meters, and so on down through the water column, and average the data within each. And that means that then all the data from each of the sections, each of the profiles will line up, and we can then apply these display functions, either the p-color or the contour. So if we switch to MATLAB, here is the folder that I've downloaded from the DLE and unzipped. If I now change into that, you can see that we've got the .cnv data files. These are converted data files from the Seabird C2D. There's a README text file which tells you the positions of the data. If we open up one of these data files, so if I right click on it and then open as text, then as before, what we can see is that we've got some header information. It tells us that column 0 is the pressure, column 1, the second column is the depth, column 2 is the temperature, and column 3 is the salinity. So now these are numbered from 0, so column 2 is the depth, column 3 is the temperature, column 4 is the salinity when we come to load them into MATLAB. The other thing we need to have a look at is further down, and when we have a look at the actual data itself, we can see that it starts on line 110. So when we load in the data using DLM read, then we're going to skip the 109 data lines. So as before, we're going to be building up a script file out of commands that we know work. So the first thing we're going to do is to read in the data out of one of these data files. So I'm going to say data equals DLM read, and then I give it the file name, which is gp1stn1.cnv. The next thing we tell DLM read is the type of the delimiter, which is white space. So we just put 2 single quotes, and then I tell it how many headlines to skip. So that was the 109 headlines we're going to skip. And then I tell it how many columns I want to skip. So I'm going to skip no columns, and that will then load in all of the data. So if we have a look over here in our workspace, I've now got 8 columns of data and 667 rows. If I have a look down here, I've got 1, 2, 3, 4, 5, 6, 7, 8 columns of data. So column 2 is the depth, column 3 is the temperature, column 4 is the salinity. So I can do a very quick plot, which is data colon comma 3 was the temperature, and data colon comma 2 is the depth. I'll then put some plus symbols in so I can show the data points, and I'm going to, that plots up the profile. I then need to flip it upside down. So that creates my depth profile. So you can see here that we've got some data up near the surface. This was where the instrument was first put in the water, and it's equilibrating with the water temperature. So that means we need to ignore some of the very near surface readings. So we're only going to use the data which is below 1/2 meter depth. That's a way of pulling out the actual profile data. And you can see from the depth profile exactly what I was saying was that the data is recorded continuously. What we then need to do is to average this data into 1/2 meter or 1 meter depth films, or whatever resolution we decide, by making a function which will do this averaging for us. So what I'm going to do now is to create a new function, and I'm going to call it bin average because we're creating depth bin averages. And again, I've typed in edit and then bin average. That means that if MATLAB already had a function called bin average, then it would have opened at this point, so I would know that I shouldn't be creating a function of the same name. I've got this message saying that it does not exist. Do I want to create it? So I go yes. And what I'm going to do now is create this function which we're calling bin average, bin underscore average, and it's going to take an input, which is the input data. So this could be the temperature or the salinity. So I'm just going to call that in. It's also going to take some depths, which I'll call D. So those are the equivalent depths to the input data. And then I'm going to tell it the depths between which I want it to do the averaging. So I'm going to call this bin ends. So this would be a vector, a list of the depths between which I want to do the averaging. So those are the 3 inputs to my function, and the 2 outputs are going to be the output data, which has been averaged, and then basically the midpoint between the bin ends that I've recorded. So dbin is going to be the average depth of the point between the two edges of the bin. So it's going to be the midpoint in the bin. Okay, next thing I need to do is to write a little description. So this is a function to create depth bin averages of profile of data, and then I can say inputs are in is the input data, for example the temperature, salinity, or whatever. You can actually average any of the parameters using this method. D is the depth of each data point, and then bin ends are the vector of depths between which to average, and then outputs are out is the bin averaged data, then the dbin is the midpoint of each bin. Okay, so this is a fairly descriptive comment up at the top of the data file. This function that we're writing now, you can apply to any CTD data. It would be useful for you hopefully for a long time into the future. So it's useful in this case to write a fairly long description of what the function is and how to use it. So what I'm going to do is to create a loop, and the loop is basically going to step through each bin in turn, and then it will find the data that falls within the depth range of one bin end to the next bin end. It will then take the average of that and put it in the output array. So we're going to step, so for that I'm going to use a for loop, and I'm going to step using a counter I from the first bin end to the last bin end. So if I go to length of bin ends, but I want to stop one short of the end, because I'm going from the first bin end to the next bin end and finding the data between them. So I need to, for the last iteration, I need to stop one short of the end and then find the data between one short of the end and the actual endpoint. Then my output for that particular depth bin is equal to the average, or the mean, of the input data where the depth is greater than or equal to bin ends I, which is the current bin end that I'm looking at. So that means that if the depth is bigger than that first bin end, then we'll include that in the average. But also, we're then saying only find me the data that is less than the bin ends of I plus 1. So I'm finding the data between the current bin end and the next bin end. So for the first example, if we're taking an average between 0.5 meters and 1 meter, then I would have fed in those two depths up here, and then it would find me the average between those two depths down here. I then need to close off my brackets. So as you see, as I enter the closing brackets, it then matches them up. So I know I've got enough there. And so this is now my output that's going to be fed back. And the second thing I need is what is the mid point between those two bins that I'm feeding in. So I'm going to say dbin of I equals but I'll just take the average of bin ends I to I plus 1. Close off the brackets, and then I can do end. Then I can save that. So this is a very short function. It's just going to step through each of the bins that I put in place, and then it's going to provide me the output. So if I go back to my command line, what I'm now going to do is to do a bin average of the data that we've collected in this plot. You can see the plot is going from 0 down to 12 and a bit meters. So if we create a series of depth bins which go from 0.5 meters down to 13 meters as our input. So I'm now going to do the temperature, which has been binned. I'm then going to get the depths, which are at those binned positions. I'm then going to use my bin average function, and the input to that is the data that I want to bin average. So in this case, I'll use the temperature, which is the third column. I need to feed in the depths, which is the second column, and then I need to give it the boundaries between each of the depth bins. So I'm going to go 0.5 as a starting point, and then I'm going to do steps of 0.5 meters all the way to 13 meters. Let's make this a little bit bigger, close off the brackets, close off the round brackets, and then I'll put a semicolon so I don't get an output on the screen. So my bin average function is now run, and you can see over here that I've now got 2 additional variables that have been created. I've got the depths, which is 25 elements long, and I've got the temperatures, which is also 25 elements long. If I now do hold on, and now I can plot the depth bins data and the temperature bin data. I'll do them as red circles, and if I look at my plot, you can see that that's gone wrong. So let's delete that line. So I can just click on the arrow, and I can then delete it. Go back to my plot. That's because I put the depth on the X and the temperature on the Y. If I swap those around, I can put the temperature on the X and the depth on the Y. You can see now that they overlay each other quite nicely. If I just untick the arrow, then those extra marks go away. So you can see that my circles here are lying over the profile and have now appeared at regular intervals. You can actually see that the near surface data is still biased by this positive value, so I think starting my averaging at a slightly bigger depth would be a sensible thing, so that we then don't incorporate this data. I might just zoom in on that part of the plot, and so you can see that 0.5 is actually slightly too shallow, so our depth profile really only starts, if we start at 0.75, that would be a better place to start. So I'm going to close that figure window. I'm then going to rerun my averaging, so I can just type the first character there, press the up arrow, and what I'm going to do is start at 0.75, but we could average over finer depth bins, so I'm going to do 0.75 in steps of 0.25, 25 centimeters up to 13. So when I rerun that command, you can see that I've now got more data points in my profile. I can do my plot of the original data. I can do hold on. I can then do my plot of the bin average data, and then I can flip the axis, and you can now see that we've got a nicer representation of this profile, which has got data points at regular intervals. Okay, so we're able to take one profile, load it in, and then plot and display it. The next thing we want to do is to step through the 5 profiles that we've make up one section, step through each of these 5 profiles, loading them in turn, doing the bin averaging, and then compiling them into a 2-dimensional matrix, which will then enable us to create either the p-color plot or the contour plot. So to do that, I'm going to start a new script. So I'm going to call this plot section. So I'm going to type edit and then plot section. Again, sanity check. MATLAB doesn't know of a plot section already, so it does not exist. So yes, I do want to create it. And I'll write a little comment, which is a script to plot a section of C2D data. Okay, up at the top I'm going to say close all and clear all, just to make sure that the decks are clear. Then I'm going to take some commands out of my history so that I don't need to retype things. So I'll just make this window a bit smaller. Actually, I'll dock the editor, and then under my environment, layout, command history, I'll say docked. And what I'm going to do is just take some of these lines in that we know work. So I want to load in a data file. I then want to bin average the data file. So this was the second way of bin averaging the data file. I then want to compile this into a matrix before I actually do the plotting. Now I'm going to undock this so that you can see what I'm doing more clearly. Now, these are the basic steps that we need. So each data file in turn we need to load in, and we then need to average it, and then we need to compile that data into a matrix. Now, to load in multiple data files, I can do that in the loop. So I can say for I equals 1 to 5, because there are 5 data files in turn. I'm then going to indent these 2 lines, and then I'll do end. So this is going to read in this data file, which is group 1 station 1, and then it's going to do the averaging of that data. So the first thing I want to do is, as I'm going around this loop 5 times, I want to update this file name here. So rather than sort of hard coding the file name, what I'm going to do is I'm going to put it in square brackets, and then I'm going to break it up into the beginning of it. So I'll put a single quote there, and then I'll put another single quote there. So we've now got the start of it, which is the group 1 station, and then I'm going to convert this counter here, I, into a string, which then can be combined with the start of the file name and the end of the file name. So I'm going to use the num to string of I. So that will sort of dynamically create the file name. It will step through each of the files that make up one section in turn, and it will load them in, and then it will do the bin averaging of that data. Now currently it's going to overwrite this tbin and dbin. So what I now need to do is to create some regular matrices, which I'm then going to feed the output of the bin averaging into. So I need to capture the output of these two, the output of the bin averager function into some extra two-dimensional matrices. Now, when we're doing a p-color plot, I need the depth information, I need the station number information, and then I also need the temperature or the salinity information. So I'm going to create three matrices, one called X, which would be the values on the X-axis, which would be the station number, one called Y, and one called Z. So the X and Y make up the horizontal and vertical data, so that's the station number and the depths, and then Z will be the particular parameter I'm plotting, so that could be temperature in this case. Now I want to create some empty matrices which just contain not numbers, because it could be that some of the data are from sections that are longer than others, so I only want to feed in data that where the profiles are long enough to actually fill in the data. So to create matrices with just not numbers in, I create some matrices with just zeros in. And I'm going to create these, so the averaging that I'm doing, I'm starting at 0.75 meters. I'm going to, let's reduce the resolution. So I'm going to go in steps of 0.5 meters, and I'm going to go to, say, the maximum profile depth that we had, I think, on any of the stations was about 25 meters. So that means that we have about 50 depth bins that we want. So let's just do a quick check of that. So if I do 0.75 in steps of 0.5 to 25, then you can see that actually I've got 49 elements within that. So I need to have 49 rows, and then I'm going to have 5 columns because there are 5 depth profiles. This is the number of depth bins that I've got, which is 49, and then I've got 5 columns, and then I'm going to divide that by 0. Now I divide it by 0 because if you divide anything by 0, that's not a number. So this is a way of creating a two-dimensional matrix, which is 49 rows by 5 columns, which is just filled with not numbers. So when you come and try and plot that, then you won't get any data displayed where there are just the not numbers. Okay, so this number here, the 49, matches the number of depth bins that I've got being generated here. I'm then going to, once I've calculated these bin averages, I'm then going to populate these matrices that I created, the X, Y, and the Z. So the X is going to be made up of basically the profile number. So I'm going to say X of colon comma I. So this is basically when I is 1, that will be the first column of data, is just made up of the value of I. And we'll change that in a minute, but we're just going to start with X being the value of the particular profile number. Y is going to be the depth bin information, so that's dbin. Now here we've got a column of data, whereas the output here is output as a row. So I just need to rotate it by using the single quote, and that will then flip it from being a row, which is the output of the bin average, into a column. So that will then fit. And then the Z is equal to in this case, the temperature bin. And again, I need to rotate that to match it. Okay, so We've now got our grids of data that have been populated, and I'm going to create a new plot, which is going to be a p-color plot, which is the first thing to have a look at, and I can do X, Y, Z of the data. So if I save that, and then I'll run it by typing plot section. Now we've got a mismatch in the dimensions here. That's because probably the size is not matching of this. So I'm going to just do a very quick sanity check of the dimensions that I created. So I'm just going to write size of tbin here, and that will then tell me the size of the output before this error. So it's 1 by 48 rather than 49, so that means I made the dimension size wrong. So I need to make this 48. And so there are 48 depth bins between these depth intervals. So now if I rerun that, you can see that we've got the makings of our plot. Now, next thing to look at is that the Y direction needs to be inverted, and also on our P color we've got these grid lines between each of the depth cells. So you can see that as depth is increasing, we're going up in half meter depth intervals, and MATLAB has drawn a box around each point. So let's fix those 2 points to start with. I don't need this size line anymore, so I'm going to delete that. And once I've done my plot, I'm going to say shading flat. So that removes the box from the display. I'm also going to do my set and then GCA and then Y direction reverse. So if I save that and then run that, and I've got an error. So line 22, I put in 2 commas there. So now if I save that, I go back and then I run that. So we're getting there with what we're plotting. Now, the next thing you'll notice is that although we've got 5 depth profiles, we've actually only got 1, 2, 3, 4 sets of data actually being displayed by MATLAB. And this is an issue with how MATLAB actually converts a 2-dimensional matrix into a p-color plot. Basically, what you're seeing here is data that is attributed to the top left corner data point. So you can see that all of the data that is within this top section up here, this first depth bin, is actually related to the value of the data which is at the top left corner. So when you get down here, you don't actually get to see the last profile at all, because it's only extending up to this 5th profile. There are other shading methods which would do a sort of an interpolation of the data between adjacent profiles. So you can do shading interp, and that would then make use of the data on this profile as well as the data on this profile to then color in the dots. So for what we're trying to do, where we want actually to display all 5 of the depth profiles, what we need to do is to actually replicate or duplicate the final column twice, which enables us to then extend our plot to also include the 5th data set. So that means that in my function here, I've actually, once I've done my loop of loading the data and feeding it in, I've got to duplicate the X data, sorry, the Z data into the final column. So I take the X data and I'm saying that all of the rows of the last column plus 1 is equal to the X data which is in the end column, but in this case I'm going to add 1 to it, and then I'm going to subtract 0.5 from that. So if you remember, the x-axis is just the profile number. So what this is now saying is that my first profile is going to be at a value of 0.5, and then my next one is going to be the value of 1.5, so that my first vertical profile is going to be centered on 1. The next one is going to be centered on 2, next one's centered on 3, next one's centered on 4, and the final one, which is not shown on this plot, is then going to be centered on 5. The y data of the end plus 1 is equal to the y data colon comma end, and then the z data of n plus 1 equals the z data colon comma end. Okay, so what this has done is it's replicated the last column of the y data and the z data identically, so that when I then go back and do my plot, you can see that we now have all the data lining up within our section, and then we've got a final set of data here in the shallows. And what this is showing, just quickly looking at, so this is the temperature, is that while we've gone through the main part of our section, we've got quite similar data, but then our final section is made up of some quite different water temperature. So this is indicating that there was a separation between the waters which were through the central part of the section. So this is, if you remember, station 1 was down in the south east, and then we were working up to the northwest. And in this case, we've got some different temperature water in the shallows at the final position. Okay, so the next thing we want to do to tidy this up is to add a color bar, so we know the scale that we're dealing with. We want to add in, perhaps change the color map. So as we're dealing with temperature, we're going to use color map of jet. We can add in a grid. We then need to add in some labels of the sections and add in a title. Okay. So we've got our P color, we're doing shading flat. We are then going to add in a color bar. We're doing changing the color map to be jet. Let's put the grid on, and then we'll add an X label, which is the station number, and the Y label, which is depth in meters, and we'll add in a title. So I'll call this example temperature, and it's degrees C. And what I'm also going to do is I'm just going to add some extra commands here on the Y direction and the reverse, so that we can essentially tidy this up. So what I want to do is, you can see that it now starts up here at a value less than 0, and also it's a bit messy, the labeling on this axis. It'd be nice just to show 1, 2, 3, 4, 5 rather than the starting at 0.5 and 1.5. So what I can say is, if I say x tick, then I say 1 to 5. That will just put the tick marks where I tell it. If I then say x lim, will tighten up the limit, so we just have a little small border around the sides. We're going from 0.4 to 5.6, and I'll also tighten up the Y limb, and we'll go from 0 down to a depth of 20 meters in this case. So I save that, run that. We then end up with a nicer display of the temperature across our section. Now you can see here that we've got the odd gap in the data, and that's because during the deep profiles the data rate was coming in quite slowly, so there were no data lines received in these gaps. So what you may want to do is to increase the bin size that you're doing the averaging within, and then so if you go back here, you might want to increase it to 1 meter depth bins, but then you'd have to decrease the actual number of values that we're capturing in the grid accordingly. I'm going to stick with the 0.5 depth bins at the moment. Okay, so we've created this version of the plot. The next thing we can do is we can create a second plot using a contour function rather than this p-color function, just so you can see how else you could display this data and what the pros and cons are of this. So in my plot section, what I'm going to do is turn this into a subplot, and I'm going to say I want 1 row, 2 columns, and this is column 1. I'm then going to copy this entire section here and then paste it. So I'm then going to create subplot 2, and then rather than a P color, I'm going to create a filled contour plot. So contour F fills the contour levels. I'm going to stick with my X limits and so on, but I need to remove that shading flat because it doesn't apply to the contour F function. So if I save that and then go back here and do plot section, so we've now got 2 displays of the same data within our file. So this is using the P color, which gives a representation of each of the vertical profiles, but what it's not doing is doing any sort of horizontal interpolation between the data. So it's not matching up data between different locations. So this is kind of showing you a true measure of where the data was recorded vertically. And then this is showing you a contour plot, which is combining the data from adjacent profiles and then plotting up the contour lines. So in this case, we've got, you can see the gradient here between the final profile, which is quite a bit cooler than the adjacent profiles. Okay, so that's 2 methods to display a section of data. We're compiling individual profiles into a 2D matrix and then using that to display it. You may wish to look at the salinity or the density rather than the temperature that we work through, but you should be able to edit the files to do that. You may wish to edit or set the limits that you're looking at in terms of the temperature range or the salinity range or the density range. You may wish to increase the depth range down to capture all of the data. I already talked about decreasing the vertical resolution, but hopefully this has given you a starting point to enable you to start to interpret the data in relation to these vertical sections data in relation to the spatial surveys that we did.